can accurately model motion by keeping track of quantities of displacement and or speed as time goes on using these formulas, but we can also create a picture which tells stories, and we can use graphs to model motion and to figure out things that are beyond what's immediately evident. When we're graphing, some fundamentals of graphing, we can plot an object's position as time goes by, and it tells us its location as time goes by. Position is the dependent variable, time is the independent variable, and usually when we compare two variables, we create a y versus x graph, and we can actually figure out the velocity based on the information presented in this. When we're creating Cartesian graphs, or when we're creating position versus time graphs, we use a Cartesian coordinate system. X is on the y-axis, the location is on the y-axis of the position, time is on the x-axis. We label the units in parentheses, so x is meters, time is seconds, and we add points, and it lets us know what's happening to the position as time goes by, or as time progresses. Similarly, we can have the same approach with a velocity graph, and this is a speed graph. It tells us what's happening to the object's speed as time goes on. And from this, we can find displacements and acceleration. So let's say if we start at a position of 4 meters and you travel at a constant speed for 6 seconds, we can determine our locations or our new positions as time goes by. Let's write the equation for speed. And we're going to assume that we're traveling with a constant velocity or speed. And we know speed is our change in distance per change in time. We'll rewrite speed is d minus d naught divided by delta t. So our change in distance would be d minus d naught, and our distance traveled will depend on how fast we're going, the speed, our starting location, and the elapsed time. So let's manipulate this equation and we'll solve it for d. D has delta t subtracted and delta t divided and d naught subtracted. So the first thing we will do, I'll rewrite s equals d minus d naught divided by delta t. The first thing I'm going to do is to multiply both sides by delta t. So speed times delta t will be equal to d minus d naught on account of the fact that the delta t's cancel. And I'll rewrite speed times delta t is equal to d minus d naught. We're isolating d, so we have to add d naught to both sides. So the distance traveled will now be speed times delta t plus d naught, your starting location. So let's make a data table. Keep track of information, times, and corresponding displacements. We're interested in keeping track of time, or the location of this object at various points in time, and those times are 0 seconds, 2 seconds, 5 seconds, and 6 seconds. So now we have an equation that we can use to compute the values for d at those various points in time based on knowing the speed, the initial location, x naught is d naught, and how much elapsed time has gone by. So in the first case, we'll solve for the distance traveled at 0 seconds. So again, that's 0 seconds is the initial condition. That's the speed, 2 meters per second, times the time, 0 seconds, plus the initial starting location, 4 meters, which was provided in the problem. So when we do 2 times 0, we get 0 plus 4 is, oh, how about that? No time has gone by. We're at the 4 meter mark. Let's apply this equation at the 2 second mark. So the distance at 2 seconds, or after 2 seconds of elapsed time, will be equal to 2 meters per second, the speed, which is the starting and ending because it's constant, times the amount of elapsed time, 2 seconds, plus the starting location, 4 meters. 2 times 2 is 4, plus 4 is 8 meters. Our new location after 2 seconds is 8 meters. The distance after 5 seconds will be the speed, 2 meters per second, times the amount of elapsed time, 5 seconds, plus 4 meters, our starting location. 2 times 5 is 10, plus 4 is 14 meters. And then lastly, we'll evaluate this or solve this equation at 6 seconds. The distance traveled at 6 seconds will be 2 meters times 2 meters per second, that is, times 6 seconds, plus 4 meters, our starting location. 2 times 6 is 12, plus 4 is 16 meters. So this gives us our positions at various points in time. Equations are storytellers. They let us know where we've been and where we will be. Alright, in this problem they're asking us to construct a displacement or distance versus time graph for an object that starts off at the 10 meter mark and travels with a constant velocity of -1 meter per second for 6 seconds. So at t equals 0, our location is 10 meters. Now every second that goes by will travel 1 meter or -1 meter. So after 1 second we would have traveled -1 meter. Our value for location now will be 9 meters. After 2 seconds we would have traveled -2 meters. So after 1 second we would go -1, after 2 seconds -2. After 3 seconds we would have traveled -3 meters. That's about the location, close enough. After 4 seconds we would have traveled -4 meters. So our new location would be 6. After 5 seconds we would have traveled -5 meters in that ballpark. Let's just adjust that one. And we'll need one additional data point, so I'll dupe it. And after 6 seconds, our new location would be -6 meters from our starting point, which is about the 4 meter mark. And it reveals a trend. We'll draw a line of best fit. And that is a downward sloping line that is straight. And that means our velocity is constant.